Hello, and welcome to today's webinar, all about GNSS interferences, how to defend, monitor, and report, brought to you by GPS World and Javad GNSS. I'm Bethany Chambers from North Coast Media, publisher of GPS World, and I will be your event manager. Before we get started, I want to let you know that today's webinar will be recorded. You are currently in a listen-only mode. The recording will be available 2 weeks from today on our website at gpsworld.com/webinars. A link to the on-demand recording will also be emailed to you when it is available. At this time, I'd like to acquaint you with the ways in which you can participate during today's presentation. Please notice in the lower left-hand corner of your console that there is a Submit button. We encourage you to ask questions throughout the presentation. Just type in the text box at the bottom left, then click Submit to place your question in queue. Many of the questions that were submitted during registration will be covered in this webinar. Some questions may also be answered in an upcoming issue of GPS World Magazine or in one of our e-newsletters. We strive to answer as many of your questions as possible. Finally, if you experience any technical difficulties during today's event, select Help to submit your issue, and assistant producer Rick Aldrich or I will personally assist you. Now I'd like to turn today's event over to our moderator, GPS World Editor-in-Chief and Publisher, Alan Cameron.
Hi everyone, it's Alan Cameron, and thanks for joining our webinar. Welcome. Today's webinar is presented by Javad Agc, who is well known to just about everyone, or most people, in the GNSS industry. He's been a continuous innovator for more than 30 years. And I saw this presentation that he's about to give. I saw it last September, or I saw an earlier version of it, I should say, last September at the ION GNSS conference in Nashville. I saw a further iteration of it at the Intergeo conference in Germany in October, and I'm very glad that we're able to present it to a worldwide audience today. I think it's of value to everyone in the GNSS industry. Bethany has already covered the way that you can submit questions during the webinar, and our plan is that Javad will talk for about 45 minutes, and then we should have a Q&A period to round out the hour. There's one question that has come in previously during the registration process that I'd like to address right away. One person wanted to know, are we going to be talking about unintentional and intentional interference? And the answer to that is yes. What Javad has to say applies to both kinds of interference. And finally, some of you may have seen a polling question as you signed on regarding purchasing decisions. That was a bug or a legacy from a previous webinar, that a slide that somehow got stuck in our electronic carousel. It is not part of this presentation, so you can just disregard that. Now I'd like to turn our webinar over to Javad Agc himself. Javad, take it away.
Okay, thank you, Alan. And ladies and gentlemen, good morning, good afternoon, good evening, good night, wherever you are on the globe. In the bottom of every slide, we have our slide number. You may want to refer to the slide number in questions that you may have. My next slide is the universe of our spectrum. There are thousands of users. There are thousands of systems, from TV and radio and everything. And somewhere in this big universe, that's where we live as GPS, GNSS users, which kind of it's in the region that I've highlighted. And if we zoom in, we get closer to where we live. And next slide, it's a more close-up of the bands for GPS L1, GPS L2, and others. So my next slide is just a close-up picture to reference the interferences. Either we have in-band as shown in the middle slide, inside the GPS L1, or we have out of band. And this, as Alan said, they could be intentional or unintentional, and we'll cover both of them. And some unintentionals are harmonics of radio stations and or TV stations and others, or intentional, as we have seen units being sold in the market for as much as $400. So there is a big difference between in-band interference and out-of-band interference. As I will cover both of them in this presentation, out-of-band is easier to deal with because we will close the windows, but if we want to deal with in-band interference, we have to remove the interference, and as part of it, we have to remove some of the healthy signals too, as we have to remove part of good organs when we remove some unhealthy or things inside the body. My next slide is just yet a more close-up of the world that we live in. I show here the L1 band. In the middle of the picture, you see GPS GLONASS band. And by the gray dots and this black wavy lines, I show that interference is everywhere. As we will show you, and the reason there was less attention to them, because we didn't know that they exist. There is rare places in cities that you cannot find interference. So this is what we need to do. We need to protect our band, because whatever we do, it's impossible to not allow others to come near our bands, intentional or unintentional. Even the systems that do exist, their harmonics falls within, very close to our GNSS bands, or close to it, or within it even, as I will show you many examples. So if we do this and we protect our bands with a filter like this, that everything outside our GNSS bands are clean, and whatever comes inside as in-band interference, we have to deal with. So if we do this, what do we get? We get better GNSS results, we protect against interferences, and we free bands for efficient use by other systems. Next slide shows what the situation that we are in. Instead of having a filter that protects us and brings all the good, healthy signals within our band and defends us against anything outside us. I'm not talking about any specific company or anything, because those specific company or the issues that came up were just an example of things that can happen, but I will show there are interferences near and inside our GNSS bands already. This is interesting for our people, for engineers. We need GPS and GLONASS. We need to have a 50 megahertz wide share of this spectrum, but because of not doing our job correctly, we are doing two things. We are bringing unwanted signals to our receivers, which is hurting our performance, and also we are not allowing other people to use this rare spectrum bands that we have. So I will talk about how to protect. How to protect first against out of band, which is simple. We introduced J-Shield, which this slide shows the shape of our filter for out of band interference. it brings all Galileo, GPS, and GLONASS L1s in and blocks out everything else with the skirt of 12 dB per megahertz. And just to show that this system, this filter is possible to bring as close as signals as light squared that we were all worried about, even as close as those, and as powerful as light squared, we can defend it. And we didn't stop at this L1 band because of the political issues that existed. We went also to the second band, because the same problems that exist in GPS L1 bands, it exists in others too. So for the other bands, we have this filter that has 9 dB per megahertz skirt. So this was for out of band. And for in band, we have a 64th order adaptive filter, which is beyond the scope of this discussion, but I will just quickly summarize that we notch out this in-band interference, and of course this works if the in-band interference does not take a chunk of our GPS L1. It is typical of 40, 50 kilohertz bands of harmonics of radio stations and TV stations. So to protect, we have in-band 64th order adaptive filter, and for out-of-band or near-band, we have J-Shield that I discussed. And also I want to emphasize that this filter was tested by ourselves, that I will explain the tools that we use, and I presented the results, test results at PNT conference in Washington, D.C. I had over 100 slides in there. Also, it was tested by independent labs of Lucent lab, Alcatel-Lucent lab. And also, I will, for the record, I say one of the largest and most powerful organizations in the U.S. that they wanted to show that this works or not. They were encouraged us to send us as fast as possible the first units that we built, and we sent them about 8 months ago, but so far they claim that they have not tested it yet. So they pretend that they didn't test it, and we pretend that we believe it. Now, the second topic is how to monitor if there are interferences, especially when there are in-band interference that nobody can do nothing about it, and even if we notch out the parts that are in-band, it will hurt by removing the healthy signals too. What was available to us before, the simplest is the spectrum analyzer, that it costs about $30,000. It needs a specialist to use it, and it's not practical to take it to the field along with your receiver when doing the actual work. Also, the more sophisticated ones were those that was used for testing light squared interference. That this is just an example of things in our lab too that cost about close to $1 million, and it's almost impossible to be used in the field and impossible by an average surveyor or GPS user. So what we do, we build inside the receiver 6, not only 1 or 2 that can be used by the instruments that I showed before, but 6 different ways, looking at the energy spectrum shape, Agc Graph, average of AGC, RMS of AGC, satellite signal to noise, and cycloslips. The first 4 items that I mentioned are looking at the signal after the RF processing and before the digital signal processing. And the second two will be on the second part, after digital signal processing. First, the energy spectrum shape. This is what I mean by the energy spectrum shape, and you can see it by a click of a button in our receivers in the field, on the screen of the receiver, or as is in this case, is through our NetHub and NetView software that runs on a PC, and through Wi-Fi or Ethernet will get connected to any receiver. This one is another, the slide that I showed you was a good example, and you saw the CA code visible through the spectrum. This is a bad example. This is real example within a city that you see. Ignore the blue line now. I will talk about it later. Just look at the shape of the spectrum of this spectrum, and you see the spectrum is completely disturbed. This is again from the screen of our Triumph VS receivers. The click of button shows that on the screen. GPS L1, it's clean, and you see in the middle, the center, the CA code component that sticks out. Again, next one is a good example, and next one is a bad example. This is what I mean by the shape of spectrum. Doesn't need much of experience on reading graphs or something. If the shape is flat with the skirts on both sides, it's good. If the center is disturbed, like the screen that you see now, it is the spectrum in-band is interfered. And these pictures are within cities of some country. For now, I will not go into details. Again, this one is another bad example. Next item is the Agc graph. Just let me explain what is Agc, maybe if there are non-engineers in the audience. We need to amplify the signal that we receive to bring it to a desired level. On this, I just put some hypothetical examples that if the desired level is 24, and the clean signal that we get has level of 4, we must multiply it by 6 to get to 24. But if the signal also has interference in it that brings it to level of 12, then we need to multiply it by 2 to get to our desired level. So it means the value of Agc and the variations of Agc can give us information about the existence and the character of interference. This one is something from our office in San Jose. The blue line is in time domain. As the previous things that I said, the shape of the spectrum is in frequency domain. It takes about 30 seconds to get this spectrum, and the blue line is the variation of Agc during that time period. So it means there was an interference at this time, maybe a little out of band, but our Agc had to work hard to deal with it. So the spectrum, the interference did exist at this time, but was not enough to disturb the shape of the spectrum that much. Next, you see the blue line in here is the Agc was quite active, and it shows the effect of energy of the spectrum also shows in this shape. Both of them together shows that the spectrum is affected and the Agc was affected in a way that shows the interference was time varying. It was not fixed. Next, again, shows a clean spectrum, and also it shows AGC was quiet, with some variations that was not disturbing much. Next one is the average of AGC. If the interference is fixed, you will see the blue line is fixed, doesn't have much variation, but its level can vary. But we have to be careful when we talk about the fixed level of AGC. We should also note that the fixed level of AGC changes by things like the length of antenna cable. So when you increase the length of antenna cable, you have to amplify more, and this can get mixed with and confused that we may have interference. So for all these cases that we want to look at the level average of a spectrum and guess on the power of interference, we need to calibrate our antenna first. To calibrate antenna first, there are two ways. One is we cover the antenna completely, and in the receiver we push calibrate, or we are introducing antennas that have this capability that you put it in the calibration mode, or you put it in the normal mode to be able to calibrate. So another item, the third item that I mentioned, is the average of a spectrum and the deviation from the calibrated. In this slide, it shows minus 1.5. This because our measurement, and when you look on the next slide, I will show the RMS. 1 or 2 dB is a level of our measurement noise depending on how much averaging we do. If you look at the same line on the top after 1.5 to the end, just before the right parenthesis, you see the number 10. It means we read the spectrum 10 times. If we read it 20 times, but for every reading will take 3 seconds. If we need more accurate reading and smoother figure, we put it 20, 30, or even 100. This is another example of our offset AGC. This is 12.4 dB of interference inside a city, inside the GNSS band. Next slide, another example. In a clean area, offset is 0.1 dB. Next is the RMS of AGC, which means what? This will show us about the nature of the interference. It was fixed CW type, or it was time varying on the slides that I showed you before. So this RMS AGC quantifies the RMS blue line figures that we were seeing before. This is another example. RMS AGC is 11.5 dB, which again is the quantified version of the blue line that we see. Another example, clean area, RMS 0.6. Next, I will talk about information that we get after digital analysis. All the things that I presented so far was looking at the raw RF spectrum. After digital analysis, we can look at satellite signal to noise. How? This slide that is again from the screen of our Triumph VS color codes the signal strength of the satellites. As we all know, the CN over signal to noise of the satellite changes according to the elevation angle. So we color code the signal to noise according to the standard, according what we expect to see. If the environment is clean, what do we expect to see if there is no interference? Blue means we are okay within 3 dB. If it is green, it means it is degraded between 3 dB to 6 dB. And if it is red, it means that signal got affected by more than 6 dB. And the next slide shows the summary, again it's from the receiver, shows the summary of everything that we talked about before. First column shows the band. Second column shows interference magnitude, which is the AGC number that you saw on previous slides. Next column is the RMS of magnitude, again, as you saw in previous slides. Column next to that, it says has signal to noise loss in the GPS L1, which is comparing what we are receiving compared to what we expect to receive. In this slide, it says 1.4 GPS L1 is 1.1 dB above the average of we expected to see. For GPS L2, minus 1.3 dB below what we expected. And next to that, within parentheses, is the RMS. And the column to the right shows signal to noise loss of the P code. And because you see more losses on the P code is because P code of GPS is encrypted. And the last column shows the number of satellites that were used for CA and P code. Next is what I call looking at the heartbeat of the patient, is looking at the cycloslip. Cycloslip is, for all high precision receivers, will rely on carrier phase measurements. CA code receivers, like for navigation and what you see in the cars, they don't use carrier phase. So cycloslip is when you during tracking, the lock point of the carrier jumps from one 0 point to another 0 point, which is very hard to detect, and it's only with extended period of data collection and post-processing we were able to see the cycloslips. Now we have a way in our receiver that instantly look at the cycloslips. And the next slide shows another screen of our receiver. On the top, 10,802 is the time that this test was going on, 10,000 seconds. And during this 10,000 seconds, this screen is for the L2, GPS L2. The average of all signals from all GPS satellites during this period, there were 38.52. So this screen can show us, or this capability can show us three things. First, if the receiver is good and there is no noise, it shows us how good satellites are. We can compare GPS, GLONASS, Galileo, and see in a clean environment which one performs better and which one has better signal to noise. In the other columns, the one that I have shown, I will just skip the rest, maybe they are obvious. It will show the number of cycloslips per satellite. And the last column is number of cycloslips per hour per satellite. So this is another thing that when it shows we are solidly tracking the carrier phases of satellites, and we don't have even cycloslip on higher signal-to-noise. This slide is organized against signal-to-noise ratio. The first column shows signal-to-noise from 50 down to 20 dB hertz. And it shows when the satellites were, for example, at 35 dB hertz, we had 0.1 cycloslip per satellite per hour. This is the time that satellite is going down. And also multipath will come into the picture. Still, it shows a very healthy environment. This, as I said, we can compare satellites together. In our San Jose office, this is a comparison of GPS L2 and GLONASS L2. Because GLONASS is not encrypted, you will see during 86,000 seconds, the average of GPS L2 is 31.24 dB, while GLONASS is 40.49 dB. Okay, now this was how to monitor. Now how to report. How people can understand where in the world we have interferences and how quickly to report it. So we don't need all those expensive equipments that I showed earlier, and the experts that needed to implement the test. And it took about a week for the previous test to provide the results and report. This, we have in our receivers two buttons, spectrum and cycloslip. This is the screen from a receiver in the field. You click a button and you will see all the data that I showed you. The other is you can connect any of our monitors on the right side, which has similar screen as our receivers. And through Wi-Fi, connect to any receiver that is connected to internet anywhere in the world, and with a click of button, see all the pictures that I showed you. You can even set up in the receiver FTP. You can click share via FTP server and FTP server settings. You specify the server IP and port and everything, and then you can, in other screens, you can say how frequently you want this to be done, so all the spectrums will get recorded automatically and will get passed to, or will get transmitted to the FTP server. The other is through our NetView software that runs on Windows, and you can connect through Ethernet again to any receiver anywhere in the world that is connected to internet and see all the screens and all the features that I explained automatically. The other is our Wi-Fi, our NetHub, that can monitor many receivers that are anywhere in the world, and also again it can be programmed periodically that how often and for how many times it can record the spectrum and all the information that I mentioned and send to any, this NetHub can view all those information through a central computer. So these are some of the screenshots from the NetView. This screen shows the summary of the spectrum. This will show, I will just quickly go through some of these slides because you saw in here I want to show that these are readily available remotely and automatically through internet. This is another slide. This will show This slide that I showed you earlier, it was through NetHub. One more of the same. Let me skip this one too. Of course, we have also polar plot of satellites. And here is the screen that I showed earlier. It color codes the signal to noise. In this picture, we color code only GPS GLONASS satellites and the signal to noise only on numbers. But the results that we show will show the offset of the signal to noise compared to optimum that we expect. This shows the cyclic slip number for 4 bands that I talked earlier and comparing different satellite systems. It shows the number of receivers that we are connected, and it shows the interval that we need to connect data and how many times we need. Next slide shows the connection to the receivers. We can monitor as many receivers as we want connected, being able to put where the data should be stored, where locally and where in FTP servers. Again, some more slides from this software. And the last one is Wi-Fi to FTP. That is an expanded version of what I taught. Many receivers are connected to FTP server, to a central server, and people can connect through email or through any other server connect to this FTP, to this site. And also we can see the locations of receivers throughout the world on a Google map. So this ends my presentation, and it will be good if we have time in the established systems that we have thousands of sites that operate as reference stations. Also add this feature that at the same time with the existing established system globally report where we have interferences. So, and this is because mostly we talk about in-band interferences that nobody is allowed to come into. This is something that it's very good if we can defend. And then people that go to do their normal job, it's good to look at the environment like a pilot that checks the weather before takeoff to see if the environment is healthy or not. In summary, we talked about how to protect in-band with 60-order adaptive filter, out-of-band or near-band with J-Shield, with the 2 filters with the skirts of 12 dB megahertz per 12 dB per megahertz and 9 dB per megahertz. How to monitor? We showed 6 different ways to do this, and also how to report. We have Triumph VS, Victor VS, NetHub, and NetView connection to FTPs, and we already have antennas for both survey and for avionics. Our AirAnt does have these protective features. Thank you, and I will be happy to answer questions. Alan.
All right, thank you very much, Javad. Very interesting presentation, and we do have several questions from the audience. Javad, if you want to look down in your chat window, I'm going to read these questions aloud, but you can read them there as well. The first question is, what companies, in case this wasn't already clear, what companies make the filters shown in slide 17 and slide 18? Are they available at this time?
These are not a single filter system. It's the line amplifier system that we built ourselves, and we use our proprietary technique, patented technique. But I don't know what the question was about a specific component, which components we use. The answer is this is not a single component. It's the combination of components put together in our special own way.
Yeah, but I believe this is it's available on some Javad receivers, or can be made available, this technology.
But yes, of course, we sell and market these in our grant type antenna, and also starting from maybe a month on our avionics antenna. FAA
okay,
kind of a shape antenna.
Yeah. So the answer to the audience question is this is technology developed by Javad GNSS, and it is available on select models of Javad GNSS receivers and antennas. Second question, someone wants to know, how wide do you think the end band notch filter can go to ensure proper operation? And they add, in other words, what is the percentage of band called narrow band versus wide band?
I use like a rule of thumb is 10%. If you cut off 10% of the band, still it's okay, 15%, 20%. As it becomes wider, then you lose your healthy signals. So something like 10%, 15%, 40 kilohertz, 50 kilohertz, as I said, typical of things that more routinely exist as harmonics of radio and TV stations.
All right. Our third question from the audience. Someone asks you to please talk about the difference between interfering with the code and interfering with the carrier.
Okay. When you interfere with the signal, you interfere with both. But carrier is more sensitive. Carrier is the one that you lose first. So it is not a distinction. I mean, if interference interferes both. Carrier goes out first.
Right. Next question. How do you estimate the expected carrier-to-noise ratio with respect to the measured value? The estimation depends on the used antenna and on the actual power of the satellite signal, doesn't it? Says the questioner.
It is both a combination of ICD, published ICD by Air Force or GPS control segment, and our experimental values. When we are in a healthy environment and we have a system that we see it matches from in general terms, matches the specifications of ICD, what we have recorded during years, and we use the average of those as our rule of thumb. And of course, all of these we can say plus minus 1 dB estimate.
We have further interest, obviously, from our audience in how to accomplish everything that you've been talking about. And one questioner wants to circle back to the first question about the availability of the filters. And this person asks, can one purchase a Javad filter or antenna to use in conjunction with a non-Javad receiver and have the filter or antenna defeat the interference as shown in your presentation? Or must one purchase a Javad receiver?
No, they can. We have different types of antennas with different capabilities. In our generic antenna that everybody can use, they can use it, our antenna, with any receiver, as was done at the Lucent test. Alcatel-Lucent Labs, that our antenna was used with the receiver of another manufacturer. But we have special features in some of our receivers. For example, calibrating the antenna for spectrum. Nobody has a receiver that does this kind of things. So if you have that antenna with the receiver that doesn't have this capability, you cannot. You can't use that feature of the antenna. Also, we have another antenna that we can calibrate the time delay through the filters and through the cables and everything that is good for timing application. Those receivers that don't have this feature, it's useless to buy such an antenna. But for all the current applications that everybody is using, survey, avionics, or whatever, general positioning, those applications that are positioning only, not for spectrum monitoring and not for timing, precision timing, they can use the antenna that I mentioned.
All right. There's going to be further questions about this aspect, but I'll circle back to that in a minute, because the next question up is, what is the data overhead of transmitting the spectrum information from remote stations?
What is the data overhead? Overhead on what? But with a regular, I just give you a rule of, the experiments that we have with one computer connecting to 30, 40 receivers, we can get data, spectrum for 30, 40 receivers without any delay. But if you say how many bits of data we need to transfer and how often, it depends on the averaging time that you use for getting any spectrum. One spectrum scan takes 3 seconds, but it will be noisy. If you scan it 10 times, it will be 30 seconds, and so on and so forth. So I usually typically use 10 measurements, 30 seconds. Every 30 seconds, you need to send this much data. I don't think with a regular Ethernet connection, bottleneck of Ethernet would be any problem, if I understood the question correctly.
Okay, we'll find out if the questioner submits any further follow-up. Javad, your company makes high-precision GPS and GNSS receivers, and the discussion has focused on high-precision applications such as survey, aviation, and so forth. And one questioner wants to know, are you aware of any small module GPS/GNSS receivers? And I think by this they mean lower precision commercial applications in consumer products. Are you aware of any small module receivers that include any jamming or spoofing detection methods?
Alan, the issue for small receivers that you refer to, you mean CA code only. CA code is only 2 megahertz wide. And it doesn't need such a sharp and filter to protect 30 megahertz and then goes down. The problem for CA code only receivers, I can tell you, is almost non-existent, because I heard there were 30 million or so cell phones that they have GPS receivers with a small filter that fits within a cell phone. They don't have this problem. It is very strange that receivers, CA code receivers, that are much bigger than a cell phone, they have problem with their CA code. With all due respect to all of them, I think they must have done something terribly wrong, that with a 2 megahertz wide system, they still they can't find a filter with a very slow skirt going down and protecting it when it gets outside of the 30 megahertz of the GNSS band. I wish I had a slide to compare. Maybe if I get a chance another time, I will compare the simplicity of a CA code only with 2 megahertz wide with the difficulty of a 30 megahertz wide that will get close to the end of the GNSS band. 2 megahertz receivers, they have 10, 15 megahertz still free on each side because it's still there within the GPS bands, even though they don't use those signals. But they are protected because for them it's considered in-band. And maybe if the caller was asking if I know anybody, receiver that does have this kind of spectrum monitoring or thinking for those receivers, I don't think so.
Right. Here's another question I think I know the answer to because the certification process is quite lengthy and laborious, but someone wants to know, do you have antennas certified for aviation use?
No, we just we introduced this, and we hope because from the physical form factor, we meet the standard. I hope with the help of some bigger companies that have expertise in this certification, they can help us to certify.
Okay. You've talked about detecting, monitoring, and reporting interference. One questioner asked could be called the $64 million question. How can you use this knowledge, or how can you find the distance and source of interference using these techniques? How can, if you find interference, what steps can you take to localize it and obviously eventually eliminate it?
Very good question, Alan. If you have, let's say, if we have in our Silicon Valley area, if every 50 or 30 or 20 miles, or in every place that there are reference stations, we have this monitoring capability that they report, and we have enough of this monitoring station. By looking at the relative power of interference as a function of distance, by triangulation, some sort of triangulation, looking at the relative power, and provided that there are a small number of such transmitters, not if we have 10 interference generator in a city, we need a lot more monitoring station to distinguish where they are. But if there are a small number of them and we have enough, it's a well-known technique of looking at the relative location of any signal and see where they are. And then when you get close, my guess is that this technique can bring us to half a mile or so where the transmitter is, and then by looking at the directional antenna, we can find in which building it is.
Okay. Someone wants to know, is the receiver calibration software to correct for signal distortions caused by the filtering, is that available yet?
Yes, it is. It's in our standard receivers that we sell. It's a feature, it's an option in the standard receivers that we sell.
Okay, and someone else wants to know, and I think this circles back to the whole concept of that we've been talking about, wants to know, does your product protect the signal or simply monitor it for interference? Or how do you distinguish between those two?
It protects against the out-of-band and near-band interference and reports in-band interference.
Right. So there's the distinction between out-of-band and near-band, and which can be protected against, and then the in-band interference. I think we've covered all the questions that have come in so far. I'm just scanning my interactive questioning mechanism, and I believe we've covered.
I came back. We got disconnected.
Okay, good. Well, in the meantime, I was just saying I think we've covered most of the principal questions that have come in. I'm going to go to a few questions now that may be slightly off your topic, but they're certainly related to it. One questioner wants to know, and this relates to a story we had recently in the August issue of GPS World, how easy is it to spoof multiple airborne targets? Again, Javad, I apologize. This is slightly off your topic, but it's related to it.
Okay, when you say how easy it is to spoof, the spoof is quite different from interference. We do nothing with the spoofing. The spoofing is we don't do anything against the spoofing. The spoofing is you create a signal that looks like a decent GNSS signal, and it has all the information, but gives you wrong information and sends you to the wrong target or right division. If you say how easy it is to jam a receiver, if, as I said in one of my presentations, maybe it was at ION, you can buy one of these $400 jammers that they sell freely through internet, and you connect to a powerful amplifier, and you make the whole city in trouble. And especially, we should note, I don't want to bring up the issue of light squared further, but it's because such a hot topic. If we are so vulnerable to something light squared that is far away from GPS, and it's a CW signal and doesn't have much power, if our receivers are vulnerable to that, we are in a bad shape, especially if our military receivers are vulnerable to light squared. It shows how ignorant we are. It means, yes, buy a $400 receiver, this thing made in China. It's sold freely through internet, connected to a power amplifier, and you wipe off the whole city. If receivers are vulnerable to signals like light squared, they sooner or later will notice that they are in big trouble. And we have to close our filter as much as we can, and then deal with in-band, the way I say, at least monitor and find it quickly where they are. But those that are airborne, they are much less vulnerable because their antenna is aimed at not on the ground, and anything that wants to interfere with them, better to be above them, to have those transmitters from ground has much less effect on them.
All right, we have about 1 minute. Well, we have a couple of minutes left, but I'm just going to submit one more question to you, Javad, that's come in from the audience. And you addressed it a little bit, but I think this person is interested in hearing it again, or perhaps taking it a little bit further. This person says, I'm interested in the amount of definition in the reporting chain. In other words, interference experience, event communicated, action taken, and that should probably be bolded, what action is taken and what effectiveness observed. This person says, I don't know that this end-to-end process has been developed. And I would agree with that person.
Okay, if you say from technical point of view, it's developed. What I showed to you, you can just, it's a product that anybody can buy, take the receivers in different cities, and program it to collect data, spectrum data every 15 minutes for unlimited amount of time and send it to FTP site. If you say the infrastructure to do such a thing, there is nothing, because this needs the effort of organizations like Homeland Security or GPS authorities in U.S. They are responsible to keep our bands clean and keep us safe.
Correct. The technology is there. The infrastructure, the enforcement is simply not in place, and to a great extent has not really even been publicly discussed. So here's a key piece of the puzzle that is missing. We can report these phenomena, and then that may be the end of the matter, at least as it stands now. So clearly this is a big challenge for all the GPS and GNSS community and the legislative bodies.
Everyone, Alan, let me just be a little frank about that. The reason is the issue of interference, such a simple issue as this, that we must protect our band, because it has ties with the political issue of light squirt. They don't want to talk about noise. When it was an issue that was political, 1 dB of interference took a lot of attention. Now when we show that this problem is not, it's our problem, and we show that already this problem exists, a lot bigger than the light squirt exists, nobody wants to talk about it because they think the issue of light squirt will surface and they need to address. That's the reason. And also, speaking of that note, let me just assure everybody that I have no financial ties with light squirt. We had a contract that ended about a year and a half ago, and they paid us some money that was not even enough to make the next one component, or I should say it was enough to make for our next generation of receivers one component. And the reason that I talk about these things openly, because this is, my discussion is only technical. This is the problem that we have, and whatever the side effect of, or political or whatever it is, I really don't care much about. And of course, I have people, as you see in my logo, they tag me as a black sheep, which I'm proud of this, to be the only one that brings this issue to the attention of the public. And someday some people will realize that the intention was all technical and no financial or any political intention was hidden in it. And did we go over past our time, Alan?
I think we're going to wind up right now, Javad. I want to thank everyone for attending. We had lots of good questions, and I'm glad we were able to present as many of them as we did. As I said earlier, in a quick scan, I think we hit all the high points, the salient questions. Once we sign off, I'll review all the questions that have come in again, and we may address them later in a print follow-up, print or internet follow-up in the magazine or the website. Javad, thank you and your staff for collaborating to produce this webinar. It's very high quality, very important topic to the entire community. And thank you to the audience for attending. We will have another webinar. Our next one is scheduled on March 7th. Just watch the magazine and the website for news about that. Thanks once again to Javad Asghji. And Javad, any final words?
Thank you so much. And as always, Alan, you're doing a wonderful job.
Oh, well, thank you. And thanks again to the audience. This is Alan Cameron from GPS World Magazine, signing off.